Hello and welcome. This is the 8581 Control Award video. I will first explain the different aspects of the robot that we programmed, and then I will show our full autonomous at the end. In the code, the robot is abstracted into 4 different subsystems: the wobble grabber, the intake/transfer, the shooter, and the drivetrain. The wobble grabber class declares 2 servos to grip the wobble goal, and 1 wobble motor. The wobble motor is a special class which encapsulates FTC's own DC motor class. Alongside the motor, it also uses a potentiometer to track the exact angle. The class adds extra functionality like motion profiling and a PID controller, which helps ensure the wobble grabber is in the exact position we need it to be. Next up we have the intake. The intake contains a motor, a lift, and a transfer. The lift class contains a go build a CR servo and a rev through bore encoder. This is controlled through a PID loop, much like the wobble goal. The transfer class encapsulates 2 CR servos. And the intake motor is, well, it's just a motor. The intake also contains 4 distance sensors. These sensors are used to coordinate the intake with the transfer so there is enough space on the robot for rings. When the distance sensor at the bottom of the transfer sees a ring, and all of the sensors at the top see no rings, the transfer allows a ring through. When a ring reaches the top, it turns a green light on. Next there is the shooter. The shooter contains 2 motors. The internal encoder of one of the motors is used to accurately track the shooter's velocity so we can correct it with a PID loop. The shooter operates in tandem with the intake and transfer to do automated shooting and autonomous. When the shooter is within a certain range of velocity values, the transfer turns on and allows the robot to shoot. And lastly, for our subsystems, there is the drivetrain. In past years, we've had issues in autonomous making the robot drive in the exact same way all the time. To resolve this, we decided to use Roadrunner, a motion planning library maintained by Acme Robotics designed specifically for FTC. Roadrunner uses PID loops and motion profiling, and also takes into consideration the kinematics of the robot's drivetrain to help it with consistent autonomous driving. It also helps us make more complex movements like turning and moving forward at the same time. Alongside all of our subsystems, we have a camera attached to the front so we can detect rings in auto. We use an open source vision library called OpenCV, partially because we have used it in the past, but mostly because the options provided by us first are simply too slow and too bloated. To detect the number of rings, we simply do a pixel count and compare that to a series of thresholds to see how many rings there really are. It's pretty basic, but considering this is the only usage of the camera at the moment, it would probably be over-engineering to do otherwise. We use all the automations above to try and make a smooth experience for our drivers in Teleop. The most useful automation is for power shots. During endgame, drivers line up at the edge of the field, press Y, and let the robot automatically move to the first power shot location. Once a ring is shot, the drivers must repress Y to tell it to move to the next location. Rinse and repeat until all the rings are shot. Throughout this video, you've also been shown a video of a tool we use called FTC Dashboard. This tool is also maintained by Acme Robotics, and it allows teams to display telemetry, graphs, and even a field map on their computer while the robot runs. We've extensively used this, particularly when tuning PID gains. With all that said, here is our full 71-point auto. With that, I hope you enjoyed the 8581 Control Award video.